Alright gang, here we go. This is for Chem 1 Unit 12, Part 5. We're talking about indicators and titrations. Alright, so indicators are pretty handy. What they are is a simple way to give us a good idea of what the pH is, or how acidic, alright, how acidic or basic our compound is, alright, or basic or compound. All right, and we'll talk more about how to calculate pH in a couple of videos here. All right. But what we can use is an indicator to help us figure out, well, what is that value, or how acidic are we? We can look at these colors, and the way it works is that you have your indicator is a weak organic acid, and when we say organic, that usually means it's got some carbon in it, probably some oxygen or something like that, and it's a weak organic acid or base, and then it has a conjugate that's a different color. All right, so here's an imaginary example here. You've got this indicator that when it's on its acid side, all right, that's when it's got its hydrogen that's attached to the indicator, all right, it's yellow, okay, and then when it's on its basic side, it turns red. And so we can, if we start with this guy, and we can turn it from one side to the next by forcing it over to one side or the other, we can, by adding in, more or less acid or base, we can switch it over and we can find out if it's yellow or red. All right, and so we can use this to help us indicate what is the solution. All right. So we have a whole slew of indicators we can use. This is just a sampling of them. So for example, one that we will use quite a bit in our class is phenolphthalein. It's right here. All right, phenolphthalein is clear when it's below about 9-ish. Okay, so it's completely white when it's in any acidic solution. But as soon as you get to about 9 on our pH scale, it starts to turn pinkish. Okay, and so really what this allows you to do is you can take a drop of phenolphthalein, put it in a solution. If it stays clear, you know you're below pH of 9, or you have either a neutral or acidic solution. And then if your solution turns like a pale pink, you know that you're at 9. But if it turns like a really, really dark pink, that means you know you're way over here somewhere. All right, some of these guys have actually two color changes. So like cresol red right up here, where'd my pen go? Cresol red. It's got a color change right here at about a pH of 1.5, 1.7, somewhere in there, and it goes from a dark red when it's less than that, and then it hits an orangish color, and then after that it kind of hits like a yellowish, and it kind of does that thing until it's up here, and then it actually goes back to red again at about 8. So it hits the orange color at about 7.9, 8ish, and then it hits the red after that. And so we can use these kind of give us an idea of what is our pH. All we have to do is take just one drop, and it'll absorb and react with what is already in your solution to give you an idea. Like bromthiamyl blue. All right, bromphenoyl blue. Where's bromthiamyl blue at? Bromthiamyl blue is a super common one because its color change happens to happen right at 7, which is super nice here. And so like in an acidic solution, it's yellow. It's this really nice clear yellow color. And then as you get to neutral, it gets this nice green color. So when you know you've got this pure green, you're right at 7. And then after 7, it turns blue. Okay. So those are indicators. Here's a universal indicator pH chart. And so what universal indicators are, it's actually a mixture of specific indicators. So instead of just having one of these, it'll mix like, 4 or 5 of these together. So you'll get a color change at each of these different pH values. So, at red or below, or, if you're red, you're at 4 or below. When you hit orange, you're at 5. 6, you're at yellow. 7, you're green. 8, you're kind of a dark green. Blue. 9 is blue. 10 is some sort of purplish color. All right, and so you can use these to help you figure out. So if you've got a universal indicator, you can put a drop of that in your unknown solution, and depending on what color you get, you can get an idea of what your pH is close to. If it's below 7, you have something that's acidic. If you're at 7, you have a neutral solution. If you're above 7, you have some sort of basic solution. All right, now, titrations is about one of my favoriteest things in all of chemistry, and it's a special chemistry technique we use to help us determine the concentration of an unknown. So if you got some solution that you don't know how much is dissolved in it, you can use a titration reaction in order to help you figure out what that reaction is. Now, in order to do this, you have to start with what's called a standard solution, and this standard solution is a known concentration. All right, so in an acid-base titration, though, and you can do a titration with all sorts of things, but we're specifically going to focus on acid-base titration because they're probably the most simple. All right, and so in the acid-base titrations, what we're going to do is we take a volume of standard, so that's our known solution, right? That's our known solution, and we're adding just enough of that to neutralize the unknown solution. Now, how do we know if it's neutralized? Well, we know it's neutralized because we're going to use an indicator. Okay, so really you're going to start with some amount of your unknown solution, and you're going to measure the volume so you know exactly how much unknown you started with, and then you're going to know the concentration of your standard and then how much of that you added. All right, and then once you reach what's called the equivalence point, okay, or your end point is when your color change happens. And once you've reached that end point when your color change happens, you know you're done adding your standard solution. All right, and so when we calculate the unknown concentration, this is the formula we're going to use here. All right, so this should look very familiar. This is very much like your dilution formula. Remember, your dilution formula was M1V1 equals M2V2. Now the difference here is our 1s are going to be our A's, so it's MAVA, and then our base, our 2s are going to be our MB and VB. All right, now the other big difference here is that we have to keep track of how many hydroxides, and then how many hydrogens our acid side and our base side have. Remember, we can have polyprotic acids and we can have bases that have more than one hydroxide. So what you're going to do, this part here, is you're just going to multiply. This is just going to be an integer number representing how many, all right, how many hydrogens does the acid have? Okay, and then this guy here is how many hydroxides does the base have? All right, so these are going to always be integers numbers, 1, 2, 3, 4, 5, 6, something. All right, probably never higher than 3. All right, and so you're going to plug those in, and then it's just a matter of solving for whichever one. Most of the time, you're going to be solving for molarity. That's the whole point, is so that we can find the concentration of the unknown solution. So you're going to either be finding the molarity of the acid or the molarity of the base. All right, now titration terms that you need to know. Okay, the titrant is the known concentration. So this is your standard that we just talked about. So this is your standard. All right. The standard, your titrant here, is going to go inside of the big long glass tube. This big long glass tube is called a burette. Okay, it's called a burette. All right. So you're going to put your standard in there because that's what you're going to be adding slowly over time. And in order to add it slowly, you're going to use this little valve. So this is a little thing that turns, okay? And so when this guy turns, it's going to be allowing the titrant to go into your Erlenmeyer flask down here. All right, and it travels through this stopcock, through and into this flask down here. Now, what's down here is your unknown, and this is the analyte. Okay, so you're using the titrant to analyze the analyte. Okay, so that's how I remember that the analyte is what you're analyzing, because they start with the same sounds. All right, now your equivalence point is the point at which the analyte has been completely neutralized. So this is that exact point where the analyte has been completely neutralized. So this is when the moles of the acid base, or the acid or base that you've added, is exactly equal to the moles of acid or base that you started with. Okay, so with whatever it depends on what you're doing. If you're analyzing an acid, then you'll put a base up here, and if you're analyzing a base, you'll put an acid up here. And so you gotta, but once you've reached this spot, this equivalence point, that's when those two moles are equal to each other. So you got a certain amount of moles of acid you've added, and a certain amount of moles of base that you had in here. Now your end point is the point at which your indicator has changed color. Okay, now if you choose your indicator well, the end point and the equivalence point should be really, really close to each other. But if you don't choose your indicator well, then the end point and the equivalence point won't be close to each other. Now remember, we have lots of different choices, so if you know your end point should, or your equivalence point should happen around, 9-ish, then it would be a good choice to choose phenolphthalein, because then you know that you've when that starts to turn pink and stays pink, you know that you're about at that pH. But if you know your equivalence point should happen at like 5, obviously it's just a guess. You're just trying your best guess if you're choosing an indicator. But phenolphthalein would be a really bad choice because it's not going to show you nothing in here. Okay, it's not going to start showing you stuff until 9. And on the flip side, if you knew it was going to change at 9, it would be a really bad choice to choose something like methyl orange, because methyl orange changes down here at like 4. Okay, so you're going to choose your indicator to help you choose the correct, match your end point to your equivalence point. Again, your equivalence point is when the moles of the acid and base are equal to each other, whatever you started with and whatever you've been adding. And then the end point is when the indicator has actually changed color. All right. So just to walk you through kind of what's going on, here's your Erlenmeyer flask, okay, and down here you've added your analyte, okay, this is your unknown concentration. Up here is your burette and your stopcock. You turn this guy, and this guy's going to start gravity's going to pull it down. So it was started up here in your burette, and then as you open this guy, it's going to start falling down this way and falling into this. Now when it hits, because you put an indicator in here, it's going to hit and it's going to change color, and then the color's going to go away after a second. And you swirl it and the color goes away, then you put more falls in, the color comes back, you swirl it, and you keep doing that until the color doesn't go away. Once that color doesn't go away, you're at the end point. And because you chose your indicator well, your end point and your equivalence point are essentially the same thing. Okay, and so therefore from that point you can use your formula to calculate what actually is the concentration. All right, so let's do this practice problem. So let's just assume this is just a titration math example problem. All right, it says calculate the concentration of acetic acid if it took 25 milliliters of 0.25 molar NaOH. So this would be this is the volume of the base, okay, that we had, and this would be the molarity of the base. And I know this is the base because it's sodium hydroxide. It says to reach the equivalence point of a 15 milliliter sample of acetic acid. So this would be the volume of the acid. Now remember, our formula, okay, is the number of hydrogens on our acid, okay, times the molarity of the acid times the volume of the acid is equal to the number of hydroxides, okay, the number of hydroxides on the base times the molarity of the base times the volume of the base. Okay, now we have to identify, what are we solving for? All right, so it says calculate the concentration of the acetic acid. So that means we're going to solve for Ma. So our Ma is going to be equal to, and we're going to divide over our Va and the number of hydrogens. All right, so it would be equal to the number of hydroxides times Mb times Vb over the number of hydrogens times the volume of the acid, Va. All right, so now we have to identify, well, how many hydroxides do we have? Well, NaOH has 1 hydroxide, so that'd be a 1. That was easy. And then the molarity of the base, well, that's 0.250. Okay, and then the volume of the base is 25 milliliters. And again, just like in dilution problems, it doesn't matter what our volume is. We just need to make sure we keep it equal. If we're going to use milliliters in one spot, we got to use milliliters in the other spot. If we want to switch to liters, we got to make sure we switch them all to liters. Now we have to figure out, well, how many hydrogens does this have? Well, this is acetic acid. You should remember acetic acid looks like this. Okay, and we talked about how this guy is a monoprotic acid. Remember, we talked about how this CH3 doesn't, these H's are not acidic because they can't get pulled off, but this hydrogen can get pulled off. So this has 1 acidic proton, so we'll say it has a 1 there, and then the volume of the acid is 15.00. All right, so all we have to do now is take 0.25 times 25 divided by 15, and we get 0.41666666666667, and so we want 3 sig figs, so it would be 0.4177 molar, okay, acetic acid. All right, so that was the concentration of our acid that we started with. And that's about it, all right, for a titration math. Now, I just want to show you a couple of tricks about reading a burette, because they can be kind of confusing at first. Now, burettes, remember, they go backwards. They start at the top and then they go down from there. Most other things that we've read, when we read a eudiometer, this was, a gas collection tube. This was is the same idea. It read from the top going down, but beakers and graduated cylinders read the other way. Okay, like graduated cylinders here, they read from the bottom going up. Now burettes are a little bit more precise. Look, so we can go to the hundredths place on this guy. All right, whereas with this specific graduated cylinder in this picture, we could only go to the tenths place. Now, when you're looking at your burette, okay, if you wanted to read this value again, you got to watch out for your meniscus. You're going to read from the bottom of the meniscus. All right, and then the thing you got to watch out for is that it counts backwards. So look, it's 24 here, and then 25 and 26. So if you're not paying attention, you might say, oh, it's less than 25, so that means it's going to be like 24.8. But look, it actually goes backwards because we started up here, and then we're going down from here. All right, and so really the value is like at a 25.200. Okay, so you got to watch out. All right, make sure you're paying attention. Or they say a 25.28. It seems generous, but whatever. And they made the measurement, not me. But anyway, so make sure you're paying attention when you're reading this, or your data is going to be really, really, really off. Okay. All right. So practice reading this guy again. It goes from 28 to 29. Okay, so that means it has to be below 28. So that our line is right here. We're going to read from the bottom of our meniscus. So this will be down here. So this will be 25.8, I don't know, 89 or something like that. 28.89. Okay, something like that. All right, and that's it for this part. So make sure you do your practice problems. That titration math can be kind of tricky. It's very, very, very similar to the dilution problems, all right? But make sure you really understand how and why we do titrations, being able to explain how it works to help us calculate the concentration. We're going to be doing several different titrations in class because I think they're awesome, all right? So make sure you do your practice problems, be ready for your checkpoint, and let me know if you have any questions, and I'll see you on the flip side.